Today I'm talking about dwarf galaxies as probes of the nature of dark matter. And what I'm hoping to cover today is why do we study dwarf galaxies? And what can these galaxies tell us about dark matter, where I'll mention satellite abundances, this strange density-pericenter anticorrelation, and my main focus will be on the dark matter density profiles, whether these are chord or cuspy. So why do we study dwarf galaxies? First of all, these objects are known to be extremely dark matter dominated. So in this figure here, I'm showing as a function of absolute magnitude, the dynamical mass to light ratio for a number of dwarfs around the Milky Way and Andromeda and some of the local group dwarfs. And what you see is that for a large number of these, the dark matter content dominates over the stars by several orders of magnitude. So the dynamics of these objects are really dominated by dark matter. We're also interested in dwarf galaxies because they're really the smallest galaxies that can form, and they live on the edge of galaxy formation. So here I'm showing the mass evolution of two dark matter halos, which are shown in brown here. And one of these halos ends up forming stars at redshift 0, and another one does not, despite having the same halo mass at redshift 0. So there are a number of processes to do with galaxy formation that we can learn about from dwarf galaxies. And finally, we study dwarf galaxies because there are just so many of them. So just within the virial radius of the Milky Way, which is approximately 300 kiloparsecs, we know of over 50 dwarf galaxies or so, and their proximity makes it particularly easy to obtain high quality spectroscopic and photometric data. And in some cases now with surveys like GAIA, we can look at motions of individual stars within these galaxies. So what can these dwarf galaxies tell us about dark matter? So the first thing I will talk about is the dark matter power spectrum, where in cold dark matter, for example, the suppression of the power spectrum occurs at 10⁻⁶ solar masses. So the smallest dark matter halo that forms in CDM is approximately Earth mass. In models like warm dark matter, the free streaming length scales inversely to particle mass. So as your particle mass gets smaller in warm dark matter, you start suppressing larger and larger structures. So what does this mean for us? So if we look at a galaxy like the Milky Way, on the left is an N-body simulation in cold dark matter, and you see that there are hundreds and thousands of small clumps around a Milky Way-like halo. In warm dark matter, you will see that as the dark matter particle mass decreases, you see less and less structures. In fuzzy dark matter, this small structure suppression is something that you expect. This is from the recent paper by Simon May and Volker Springel, where they actually have a cosmological simulation in fuzzy dark matter, and they do see the small mass structure suppression. So in this case, this is less to do with free streaming length, but this is rather the suppression due to quantum effects. So this brings me to the missing satellites problem, which is one of the original small-scale problems in CDM that has really motivated new dark matter models. And on the left is again a Milky Way mass halo in cold dark matter, where you see thousands of small clumps. And on the right, I'm showing you a movie of the discovery of Milky Way satellites. So in principle, you would expect all of these small clumps to potentially host a dwarf galaxy. We know of about 50 satellites or so of the Milky Way. Most of them have been recently discovered with surveys like SDSS and DES. And this number of 50 is way too small compared to what we expect in CDM. So does this mean that we need an alternative dark matter model, like warm dark matter or fuzzy dark matter, where we get rid of some of the smaller clumps, or are we missing something else? So one thing you would notice from this figure here is that a lot of the dwarf galaxies seem to be above and below the plane of the disk. So this is because these really small faint galaxies are really hard to see when you're looking along the plane of the disk. Another thing is you see that their distribution is mostly concentrated towards the center. And that is essentially an effect of our survey magnitude limits. So if you have a very, very faint galaxy that is too far away from you, your survey might just not detect it. And this brings me to the galaxy formation processes and what effect would that have on the number of satellites that we see around Milky Way-like galaxies, and therefore, whether there is a need for warm dark matter or not. In particular, we're interested in constraining this stellar mass-halo mass relation. In this plot, this is actually a relation between stellar mass and the peak circular velocity that a halo would have. And on the left, the different points are results from the Apostle suite of simulations. And on the right, there are results from fire simulations. And these seem to follow completely different relations in terms of the stellar mass and the peak, where for Apostle, you see that there is some sort of a cutoff relation. So none of the halos with V peak below 20 or so can form stars. Whilst on the right, you see that even for these small halos, some small galaxies can form. And this has huge implications for the number of satellites that we expect around Milky Way mass galaxies. So if you assume that this cutoff relation is correct, then we may have already detected all of the satellites that there are around the Milky Way. If, however, this relation has more of a power law form, we expect to see hundreds more. So I think the conclusion here is that we really need to understand questions like, what is the smallest galaxy that can form? And what is the smallest halo that can form a galaxy before we can use satellite counts to constrain, to rule out cold dark matter, for example. Okay, and now I would like to move on to one of my favorite questions. This is the core cusp problem in cold dark matter. So historically, it has been known that n-body simulations predict that dark matter halo profiles have this NFW or cuspy shape. So where the slope goes as r to the -1 in the central regions. Whilst some measurements of galaxy rotation curves have generally favored profiles where there was a constant density core in the central regions, so the slope is 1. So again, does this mean that the cold dark matter model is incorrect, or do we need alternative dark matter models to try to explain this chord profile shape? So at this point, I would like to distinguish between the different types of dwarf galaxies that I'm going to mention in this talk. One is the dwarf regulars. These are generally more massive dwarfs like LMC or WLM, which are supported by rotation. So the dark matter distribution is usually inferred by rotation curves. And the other type of galaxies is the dwarf spheroidals. So these are typically the galaxies that you will find within the virial radius of the Milky Way that have this sort of spheroidal shape. And these are generally supported by random motions rather than rotation. And of these, I also differentiate between classical dwarfs. So these are just more massive dwarf galaxies like Sculptor and Fornax that we've known about for a while. And the ultra-faint dwarfs, where the stellar masses could be as low as 100 or 1,000 stellar masses. So the evidence for cores comes primarily from rotation curves measurements in the dwarf regulars. So here is a fairly famous plot from O et al. Showing observations of nearby dwarf irregular galaxies. And on the y-axis is the slope of the dark matter in the central regions of the halo, where 0 would be a core and -1 would be a cusp. And you see that there are a number of points here that are consistent with an NFW profile, but it really seems that the majority are clustered around chord halos. So at this point, I would like to mention the sort of different things that might go wrong when you're trying to model rotation curves. So this could be offsets between the photometric and kinematic centers, non-circular motions, projection effects, gas pressure, substructures, supernova bubbles, or you might infer inclination of the galaxy incorrectly. And a kind of interesting thing is that all of these issues that can happen when you're trying to model these galaxies, they will all bias you towards cause. So if there is in reality an NFW halo, and you have one of these problems affecting your measurement, you will incorrectly infer a core. And I think there is a good number of galaxies where, on the surface, they seem kind of well behaved, and there is no reason to suspect that something is going wrong there. But I think the fact that all of the bias seems to be going one way is something to worry about. So how do we make cores? Obviously, the core cusp problem has been a great motivation for alternative dark matter models like self-interacting dark matter and fuzzy dark matter. But you can actually also make cores with just the baryonic processes that happen within galaxies, for example, through supernova feedback, which I would like to focus on today. So how can you make cores in supernova feedback? So assume you have an NFW halo, and this halo is accreting some gas, and this gas becomes very cold and very dense, and it forms stars. And then some of these stars will eventually go supernova. And as this supernova explosion occurs and the gas starts getting driven out, for a dark matter particle on some initial orbit, the gravitational force is now insufficient to keep it on the orbit, and this particle will migrate outwards. And if you have this process happening over and over again, this dark matter particle will keep migrating to larger and larger orbits. And so you can eventually create a dark matter core. And actually, there's been a number of now cosmological simulations where you have, say, a box containing a Milky Way-like galaxy and a number of dwarf spheroidal galaxies, where they actually find this process to be important. So on the y-axis is again the slope of the dark matter density in the central regions, and on the x-axis is the ratio to stellar to halo mass. And what these simulations find is that as you increase the stellar mass, this process becomes very efficient, and all of these bright dwarfs will form a core. While if you have something like a classical dwarf galaxy or an ultra-faint dwarf galaxy, you never form enough stellar mass, and therefore you don't get enough supernova, and you will have a cusp. I should mention at this point that not all simulations predict this relation. And a key issue here is how do different simulations model the galaxy formation process. We cannot resolve individual stars. So effectively in a simulation, a star particle actually represents a stellar population with a mass of about 10 to the 4 or so. So we have to use what we call subgrid models to model processes like star formation, which effectively happen below the resolution limit of the simulation. And one of the important parameters there, it turns out, is this n parameter that is the density threshold for star formation. The density threshold for star formation is how dense do you allow your gas to get before it starts forming stars. And if this density threshold is low, your simulation does not predict core formation at all. If the density threshold is high, you predict that cores form. And actually, some of the more recent works have now looked into this in more detail, Actually, the density threshold for star formation is not as important as you really resolving the interstellar medium within a galaxy, where your galaxy gas has a cold, a warm, and a hot phase. And if you can get this cold gas, it will become dense, and it will eventually form stars and go supernova, and you will form a core. So the key here is to try to get this really cold and dense gas that we know is what happens when stars form in the universe. So it really seems that the closer that we're getting to actually modeling star formation as closely as possible in our simulations to what happens in the real universe, the more it seems that cores are actually a natural outcome. So now hopefully I have convinced you that we know that there are stars in galaxies, and we know that there are these some of the stars that go supernova, and this is actually something that has been seen in observations, so we know it must have some effect on the galaxy. The simulations that try to model all these processes as closely as possible suggest that in these galaxies we will form a core. But now, how do we distinguish between a core that forms because of supernova feedback, for example, versus a core that would form in, say, self-interacting dark matter, where for a different interaction cross-section, you start forming cores of bigger sizes, for example. And so the key here is that in models where cores form through supernova feedback, this is really dependent on how long has star formation been happening, and so how many supernova you have had in the history of this galaxy. So when we talk about cores that are created through supernova feedback, what we mean is actually there is initially an NFW cusp that then just keeps getting shallower and shallower until you form a core. While, say, in self-interacting dark matter, the core is always there. And so this paper by Justin Reed in 2019 tried to look for signatures of this supernova feedback causing core formation in dwarf galaxies. And you remember that I told you that in bright dwarfs, this process is expected to be efficient. And in most of the dwarf spheroidals and the ultra-faint dwarfs, we expect to find cusps because you just never form enough stars to create a core. So I would like you to focus on the central figure here, where on the y-axis is the density of the dark matter distribution at some very small radius, and on the x-axis is halo mass. And now the squares here are the dwarf irregular galaxies. These are the galaxies in which we expect to see cores. And the circles are the dwarf spheroidal galaxies, so the ones where we expect to see cusps. And the gray band here is just a consequence of the mass concentration relation in lambda CDM. So for a given halo mass, there is a range of concentrations, and so there is a range of densities that you expect. And now the points here are colored by how long has the star formation been happening in these galaxies. And it would really seem that in those where the star formation has been ongoing for a very long time, the central densities are more consistent with core-like values. And in dwarf spheroidals, where star formation has been truncated a long time ago, you see more cuspy-like densities. So are there actually any convincing detections of cores in dwarf spheroidal galaxies? So firstly, I would like to tell you about how do we usually infer the density profile in a dwarf spheroidal galaxy. For dwarf irregulars, this is done with the rotation curves, but for the dwarf spheroidals, we're now looking at the motions of individual stars. And the classic approach to this is to use the spherical genes equation. So on the left, you see the distribution of stars in 3D. So usually we just have the projected stellar profile. So we would need to deproject that then. We also have the radial velocity dispersion and this anisotropy parameter beta, which is the ratio between the tangential and the radial velocity dispersion. And this is something we don't really know. The velocities that you observe are the line of sight velocities. And in this equation, you really need the 3D information. Now with surveys like GAIA and some of the more nearby dwarfs, you actually start seeing the velocities along the plane of the sky. But this is really something that you can maybe do for ultra faint dwarfs, for which are really close by, but for which there is otherwise just not sufficient data. And so we have some model for this anisotropy parameter beta, and then we try to infer the mass content. And by doing this, we make a number of assumptions. So the first is that dwarf spheroidal galaxies and their dark matter halos are spherically symmetric. We assume that the galaxies are supported by random motions and not by rotation, and we assume that these galaxies are in equilibrium. And back in 2011, a work by Walker and Peñarrubia actually used this Jeans equation approach, and they have claimed to be able to rule out NFW cusps in sculpture and fornax at high significance. So they took advantage of this property of some of the dwarf spheroidal galaxies, where they seem to have this centrally concentrated metal-rich population and a more extended metal-poor population of stars. And these stars also have different kinematics. So the metal-rich component seems to be more kinematically cold with a lower velocity dispersion, and the metal-poor population is more kinematically hot with a higher velocity dispersion. And now, since you have these two independent tracers of the gravitational potential, you can apply the Jeans equation to the metal-rich and the metal-poor population, and then get a better constraint on the dark matter profile. So they actually used a slightly simpler version of this. They used a property of the Jeans equation where pretty much independent of what your anisotropy parameter beta is, you can obtain the mass within the half-light radius of the galaxy at a very high accuracy. And all you need is the line of sight velocity dispersion and the half-light radius, which are both measurable quantities. And so Walker and Peñarrubia used this to estimate the mass for the metal-rich and the metal-poor population within their half-light radius. So they get two masses at two radii, and then they can draw a slope, and then the slope tells you whether you more likely have a cuspy profile or a choric profile. And so for sculpture, they've been able to reject the NFW cusp at 99% significance, and for fornax at 95% significance. So in my work in 2018, I actually used the same method, which I applied to a large sample of dwarfs from Apostle simulations. And what I found is that in general, this method is fairly robust, but there are some exceptions. So for example, you can have this metal-rich population of stars and metal-poor populations of stars, which are not spherical, but say they're both ellipsoidal to the same extent. And when you apply the Jeans equation will be biased, but it will be biased to the same extent in the metal-rich and the metal-poor population. So then the result you actually get out is unbiased. But then you could also have a dwarf galaxy where the metal-rich population is really spherical and the metal-poor population is more ellipsoidal. So then when you look at this galaxy along different lines of sight, you will infer completely different slopes. And so we found that in about 20% of cases, and the halos, the dark matter halos are NFW in these simulations, in 20% of cases, we found a profile that was shallower than an NFW. And in 4% of cases, we would find that the method returns a hole in the central region. So it's not even a core, but the density is decreasing further towards the center. So sort of in lieu of this, let me get back to what are these assumptions that we typically make about the dwarf spheroidal galaxies when we apply the spherical Jeans equation. So first of all, we assume that these galaxies are spherically symmetric, and that is actually just not true. So local group dwarf galaxies are known to not be spherical. For example, Fornax has an ellipticity of 0.3, and actually when we plot the isodensity contours for different stellar populations in this galaxy, for example, the red clump stars or horizontal bright stars, you see that there is significant misalignment between the different populations. And you also see some lopsidedness. So not only are these things not spherical, and Fornax is only one example really. Here's a sort of a census of some of the satellites of the Milky Way, where this epsilon parameter tells you the ellipticity, and 0 would be completely spherical. And you can tell with these numbers that none of the Milky Way dwarf spheroidals are really near spherical. And what is the effect of this when we apply the Jeans equation? Well, if you have this ellipsoidal galaxy and then you start looking at it from different lines of sight, so along one direction, it will actually seem quite spherical in the sky. Along the other direction, it will be quite elliptical. Depending on your line of sight, whether it's along the minor, intermediate, or major axis, you will get completely different results. And I should say there are methods nowadays that have moved away from the spherical Jeans equation. So, for example, in this work by Hayashi et al., they used instead of spherical symmetry, cylindrical symmetry. So now you don't assume that the galaxy is spheroidal, but you rather say that it's axisymmetric. And what they find is that you could fit a core in some of these profiles, like the sculpture or for Fornax, but all in all, the density profiles are still consistent with cusps. Secondly, I mentioned that we often assume that the galaxies, the dwarf galaxies, are supported by pressure or random motions and not rotation. And actually now with Gaia EDF3, it has become possible to look at the motions in the plane of the sky in some of these galaxies. You really have to generalize over some samples of stars, because for individual stars, you can't really get very accurate. The error bars are just too large for the individual stars, but now you can see that in dwarfs like Ursa Minor and Sculptor and Fornax, we see some rotation in the plane of the sky in all of these. So simply put, the assumption that these dwarf galaxies are completely supported by random motions is just not correct. And the effects could be different depending on how do you observe this galaxy. If it's rotating, if you're looking at Adjon, you will likely overestimate the mass. But for example, if you're looking at a dwarf galaxy that's rotating on the plane of the sky and you're applying the Jeans equation, you will significantly underestimate the mass in this galaxy. And we actually believe this is something that might be happening in Carina dwarf galaxy. And finally, using the Jeans equation, we assume that these galaxies are in equilibrium. And that is also not necessarily correct. I talk about Fornax a lot. It is my favorite galaxy, but it is a good demonstration. For example, there are, the galaxy is not really smooth. You do see some overdensities. You see globular clusters. In this plot, the shells in Fornax are marked. And I have previously shown you this plot showing rotation in Fornax. You can see the rotation is generally happening in the clockwise direction, but there is one exception where the stars seem to be moving in the opposite direction, which actually coincides with a known shell in Fornax. And this could mean a number of different things, but a very likely explanation is Fornax had recently had some kind of minor merger, which would mean that this galaxy is not necessarily in equilibrium. And of course, as I mentioned in the beginning of my talk, the reason we look at dwarf galaxies so much is because they are quite nearby to us and they are within the virial radius of the Milky Way. But what that means is when these dwarf galaxies fall into the Milky Way, they become susceptible to the actions of galactic tides. So that means that first, the dark matter will become stripped from the edges of these halos. And as it becomes more and more stripped, the stars will also become affected. And if this really has a significant effect on the stars, we should be able to see stellar streams around these dwarf galaxies. That is not always possible because, you see the dwarf galaxy because it's a good overdensity on the sky, it is bright, but the stellar streams you might not always be able to see just because of the brightness, for example. So it's hard to tell whether some of these galaxies might or might not be affected. And finally, I wanted to bring up that, we might not necessarily even have enough data, even for dwarfs like Sculptor and Fornax, which are very bright, and we have significant star samples of something like 3,000 or so stars. This might simply not be enough to get any conclusive inference of a core or a cusp in this galaxy. So this is a work by Chang and Nesib in 2021, where they took mock galaxies. One of them is a cuspy galaxy, another one is a chord galaxy. And they took samples of stars from this galaxy and applied the Jeans equation to them. And I should mention that in this analysis, they assume full knowledge of the anisotropy profile. And what they find is you really need samples of more like 10,000 stars to give you some kind of conclusive result. So if you have a galaxy that actually has a core, you will need something between 1,000 and more stars to actually rule out a cusp completely by applying the Jeans equation. There's also a kind of important consequence to this work. When we're trying to see how sensitive we are to the dark matter masses and annihilation cross sections with observations like one would do with Fermi. So the probability of detecting some byproducts of dark matter annihilation are directly related to the density profile squared, which is something you get out of the Jeans equation. If you don't have enough data, you will have bigger error bars on this J factor. But also, if you in this work they show that if your priors are also not wide enough, so the priors are the values that we assume the density profile could take, for example, if the priors are not wide enough, you will also get artificially small error bars on the J factors, which will make your sensitivity curves a bit more constraining than they actually are. So that is kind of an important consequence of this work. I think I'm slightly running out of time. So I'm gonna quickly move on to the density pericentre anticorrelation relation that has been observed in dwarf spheroidal galaxies. So this is a paper by Kaplingat et al., where they've measured central densities for a number of dwarf spheroidals, and they plotted these as a function of pericentre. And what they see is that the dwarfs with lower pericentres have higher central densities. Now, this should be counterintuitive based on what I told you about, dwarf galaxies falling into the Milky Way and their dark matter getting stripped and therefore reaching lower densities. So actually, this could be a manifestation of self-interacting dark matter. So from what I have shown you before, in self-interacting dark matter, you expect cores to form. This is true, but also after that, the self-interacting dark matter halos will enter a core collapse phase, where the core now shrinks and becomes more dense. And this process will become accelerated when a dwarf galaxy is within a tidal field. So actually in self-interacting dark matter, this is exactly the sort of relation that you would expect. So as this self-interacting dark matter halo is getting more and more stripped in the Milky Way potential, it would then be expected to become denser. So this could in principle be a problem in cold dark matter. I will explain in a minute why it is at the moment not. But just to mention this work by Correa et al., who looked at the density-pericenter anticorrelation, and they came up with a velocity-dependent cross-section model, which would fit all of the dwarf galaxies that are being analyzed in the Kaplan-Gap work. And it seems actually very neat that they're all well described by this relation. What they do find, however, is that the Milky Way mass is very important in the study. So the density-pericenter anticorrelation exists because we think we know what the pericenters of the dwarf galaxies are. And we do know proper motions quite well from Gaia, but the pericenters that you then get out of the proper motions are dependent on your assumption of the Milky Way potential. And we do not know the Milky Way mass very well at all. So actually the density-pericenter anticorrelation can go away if you change the mass of the Milky Way to some extent. So would this relation in the work by Correa et al. Still, do we have a way to explain this strange anticorrelation within the cold dark matter model? This has previously been covered in Hayashi et al., where they used dark matter-only simulations, and they showed that basically for higher initial circular velocities, V peak, you see higher densities, but then also as you go to lower pericenters, it seems that you find less and less dark matter halos with low densities. So actually, this is a consequence of tidal effects within a galaxy. So if you have a low density dwarf galaxy, low density subhalo falling in, if it gets really close to the center of the Milky Way, if it has a low pericenter, it will get destroyed. But if you have a higher density subhalo, it will survive. And so you do see an anti-correlation in cold dark matter, which is essentially a consequence of this survivor bias. I have also looked at this relation in the Apostle simulations of dwarf galaxies and Milky Way-like halos. And I also am able to find this anti-correlation and actually statistically comparing this power law slope that you can fit through this relation. It is within 2 sigma consistent with what Kaplan-Gap et al. Finds. And an interesting thing here as well is that the yellow dots here, again, are the density-pericenter anticorrelation as found by Kaplan-Gap. If instead we use the axisymmetric genes modeling values derived by Hayashi et al., the correlation is no longer very strong. And if we plot the ultra-faint dwarfs, they really don't lie on the same power law relation as the classicals. So I think from the data so far, it would seem that the densities of the ultra-faint dwarfs and the classical dwarfs within the Milky Way are well consistent in simulations in cold dark matter. Okay, so I'm going to leave you with my conclusions. I hopefully have convinced you that dwarf galaxies have some very important information about the nature of dark matter, and they're very good places to look for dark matter because of their high mass to light ratios and their relative proximity. Missing satellites and forecast problems in CDM have sparked interest in alternative dark matter models, but hopefully now I have also shown you that you can solve these problems within CDM with the inclusion of galaxy formation processes. And now, of course, that we still have not detected dark matter, it is becoming more and more important to distinguish between what would be the observable effects of alternative dark matter versus the effects of galaxy formation itself. Okay, thank you.